Hey everyone, welcome to The Explainer. Today, we're diving into a really massive piece of AI news. We're talking about the intersection of machine learning, automation, and the future of autonomous vehicles. We're going to look at a totally groundbreaking way that self-driving AI is actually learning about the world. It's called AG-level JEPA, and it is, literally, rethinking how we sift through the absolute mountains of data our cars collect every single day. I am so pumped to walk you through this because the way this model learns is just incredibly elegant. Let's get right into it. But first, I want to pose a paradox to you, something that is literally keeping engineers awake at night. How on earth do you find the edge cases in millions of hours of raw driving data? Think about it. Every single day, autonomous test fleets are out there capturing massive amounts of telemetry. But let's be real, 99% of that driving, it's just a car going straight down a highway. It's routine. It's kind of boring. The real value, those safety-critical scenarios that actually teach the AI how to drive better, they're hitting. It's like finding a needle in a massive digital haystack. And finding them is arguably the biggest bottleneck in the entire self-driving industry right now. Okay, let's dive into this. Here is our roadmap for today's explainer. First up, the data bottleneck. Second, introducing AGL-JPA. Third, the surprise mechanism. Fourth, benchmark proof. Fifth, developer integration. And finally, we'll wrap up with limitations and outlook. Section 1. The unlabeled data bottleneck. Finding that needle in the telemetry haystack. Now, to really appreciate the genius of this new solution, we first need to understand why finding that needle is so incredibly difficult and expensive. We're facing a pretty stark contrast here between traditional methods and the wild reality of modern fleet telemetry. Traditionally, to figure out if a driving scenario was complex or dangerous, we basically had to rely on human annotators watching videos, supervised classifiers, or these really rigid handcrafted rule sets. But there's a fatal flaw here. All of these methods require a ton of prior knowledge about what actually makes a scenario difficult. Plus, human annotation is just painfully slow and super expensive. Then you look at the other side, the reality of fleet telemetry. We're talking massive scale. It's mostly routine, and crucially, it is completely unlabeled. The traditional methods simply cannot scale to process this absolute fire hose of raw, unlabeled data. Moving on to Section 2, introducing AD-JEPA, a self-supervised breakthrough. This is a model detailed in a recent paper, Archive 2606-2838, for those keeping track, and it completely flips the script on how we process all this telemetry. Let's define the core technology driving this whole thing, JEPA. It stands for Joint Embedding Predictive Architecture. Now, this isn't your standard neural network. Instead of trying to recreate raw pixels or, perform explicit object detection, a JEPA model does something entirely different. It learns to predict latent representations of future states based on past observations. Basically, it compresses the world down into a latent space and then minimizes prediction errors right there within that space. This is highly, highly efficient because it just ignores all the irrelevant background noise and focuses purely on the underlying dynamics of the environment. Which brings us to the core claim of this research. It's perfectly captured in this quote right from the paper. The model can discover scenario complexity on its own, with no labels at any stage. I mean, wow, that is the zero label breakthrough right there. The AI is not being told what a dangerous intersection looks like. Nobody's feeding it a list of known edge cases. It's just processing structured agent state data and figuring out the complexity completely organically. All right, Section 3. The surprise scoring mechanism, measuring AI prediction error. Because you might be wondering, how exactly does an AI discover complexity without any labels? Well, it turns out it all comes down to how well the AI can predict the future. And this brilliantly illustrates the step-by-step logic loop the model is actually using. Step 1, the model ingests a sequence of agent states. Think of this as the recent history of where cars and pedestrians have been moving around. Then Step 2, it uses its learned world model to predict the future latent state. Step 3 is where the magic happens. It calculates the temporal prediction error. Basically, it's comparing what it thought was going to happen against what actually happened in the data. Finally, Step 4, it uses that error to spit out a scalar complexity score. It just takes the mean squared prediction error across the time horizon, and boom, that number is your score. To put this into a more human context, the researchers are essentially using this temporal prediction error as a stand-in, a proxy for complexity. When the model encounters a high error, it's basically experiencing surprise. It really struggled to anticipate what was going to happen next. What kinds of scenarios cause this? Things like unprotected turns, tricky crosswalk interactions, cars getting too close to pedestrians. Unpredictable stuff. Conversely, a low error indicates boredom. The model perfectly predicted the future because it was just standard lane following or sitting in stationary traffic. The whole architecture naturally filters out the boring data and flags the surprising, high-variance interactions. It's pretty genius. Okay, Section 4, Benchmark Results and Proof. Validating the complexity proxy. Because, hey, theories and human analogies are great and all, but does this zero-label scoring actually work when you test it against real data? Now, what's really interesting here is the hard data. The real proof lies in the downstream anomaly detection evaluation, which they ran on the nuPlan mini dataset. We're looking at average precision, or AP. The chance baseline, which is essentially just guessing, is sitting at 0.436. But the JEPA zero-label score, it achieved an AP of 0.512. That is a really significant performance gap. It proves that this temporal prediction error isn't just random noise, it's effectively capturing meaningful structural differences in driving scenarios. And the craziest part, it did this without requiring any threshold tuning against labeled ground truth. No hand-holding whatsoever. Just to be absolutely certain the signal was real, the researchers ran 4 controlled ablation experiments. They systematically stripped away pieces of the pipeline. What did they find? They confirmed that the signal absolutely originates from the temporal error. If you remove the predictive objective entirely, the scoring distribution just collapses. It becomes totally useless. And if you try to replace the latent space with a supervised classifier, you instantly reintroduce label dependency, which completely defeats the entire purpose of the zero-label approach. So these ablations prove, for sure, that the architecture is doing exactly what it claims to do. Section 5, Developer Integration, Implementing the GitHub repository. For all the engineers, data scientists, and builders tuning in right now, you're gonna love this. The team open-sourced their reference implementation, and it is ready for you to experiment with today. Let's see how this builds out in practice. The official repo is up on GitHub under Haran Zhu Explorer/Adla JEPA. The workflow is actually highly modular. First, you set up the Docker environment to make sure everything is perfectly reproducible. Second, you run the training script to ingest those nuPlan's mini-agent state sequences. Third, once it's trained, you use the scoring module to batch process your own unlabeled telemetry. And finally, fourth, it outputs your complexity scores right alongside the sequence IDs as a CSV or Parquet file. You can literally take this output and pipe it straight into your data curation workflow to automatically flag those high-complexity, needle-in-the-haystack segments. A quick note on the technical requirements, because they are pretty specific. It's built on Python 3.8, and it explicitly asks for PyTorch 1.10.1 plus Q11.1. The documentation heavily advises pinning these exact dependency versions in your requirements file. Why? To prevent what they call latent space drift across PyTorch updates. If that happens, it could silently alter your complexity scoring, and you definitely don't want that. But the repo includes everything you need. It's separated cleanly into modules for pre-processing, training, and inference. It even lists pre-trained weights for datasets like Kitty3D and ONC. Just keep in mind, you'll be training the JEPA complexity scorer itself on your own hardware. Bringing us to Section 6, Limitations and Future Outlook. Guardrails for application. Because as powerful as this breakthrough is, we always need to look at the guardrails and understand the actual boundaries of the current research. So the crucial point here is that this is a triage tool, only a triage tool. A high complexity score just means the AI had difficulty predicting the future. It doesn't automatically guarantee an increased collision risk. You absolutely cannot use this as a substitute for safety validation. Also, the current evaluation is confined strictly to the nuPlan mini dataset domain. We honestly don't know yet how accurate this scoring is in the wild, like in mixed traffic environments or during really bad weather. And finally, the model assumes state transitions are adequately sampled during training. So if your training data is super sparse or heavily skewed, your complexity scores are going to be pretty noisy. But listen, even with those limitations, this represents a truly massive leap forward for AI autonomous driving. Which leaves us with a really fascinating forward-looking question. How will zero-label world models fundamentally change the future of AI testing and simulation? If we can automatically triage millions of hours of driving data without a single human label, we could accelerate the development of autonomous vehicles exponentially. It's a fantastic piece of AI news and just a brilliant architecture. Thank you so much for joining me for this explainer. I really encourage you to read the full Archive paper and check out the GitHub repo to see the code for yourself. Keep learning, and I'll catch you in the next one.